The phase-velocity paradox centers on a physical contradiction. While Maxwell's equations predict electromagnetic waves travel at light speed, these waves move much slower, behaving instead like a heavy, vibrating string. To understand why light behaves as if it has physical weight, we have to look at the geometry of the plasma environment. The Swedish physicist Hannes Alfvén won the Nobel Prize for proving the mathematics behind this behavior. He demonstrated that magnetic fields embedded in a plasma environment possess a literal, calculable tension that forces the field and fluid to move as one. This diagram sets up the geometry required for that coupling. We start with a 3D coordinate plane. The thick blue vector represents a uniform, static background magnetic field, called B0, running straight up the z-axis. For an Alfvén wave to exist, the wave propagation vector, k, must run perfectly parallel to that background magnetic field. Meanwhile, the wave's oscillating electric field, E, is strictly constrained to the perpendicular x-axis. Because of this parallel alignment, the electromagnetic wave cannot propagate independently. As it moves, the field lines act like physical rails, dragging the surrounding charged plasma fluid along with the wave's oscillations. We begin the derivation with classical electrodynamics. This document shows the starting point, taking the curl of Faraday's law of induction, expanding the double cross product of the electric field, and substituting in Ampere's law gives us the electromagnetic wave equation. The expression on the right side introduces the current density, J, which represents the response of the plasma particles to the wave. To solve this, we use plane wave notation to convert calculus into simple algebra. Time derivatives are replaced with negative I omega, and spatial gradients become ik. Applying these complex plane wave rules to the spatial and temporal derivatives streamlines the expression. We replace the derivatives with our new omega and k terms. Now we apply our specific geometry. Because the wave vector k travels along the z-axis and the electric field E oscillates on the x-axis, they are perpendicular. Their dot product is 0, which eliminates the first spatial term from the equation. This leaves us with a master equation. It links the wave's frequency and wave number on the left side to the plasma's current density J on the right. But the derivation is stuck because the current density is an unknown variable. To solve for the wave's velocity, we must determine how the plasma fluid generates that current. Plasma current is driven by the physical separation of charged particles. To find J, we must first determine how the massive positively charged ions in the plasma react to the oscillating wave. We calculate this using the ion fluid equation of motion. It states that the mass of the ions times their acceleration is equal to the Lorentz force acting on the particle density. To isolate the wave's transverse motion, we expand the cross product for the x-axis. This extracts a new velocity term, UIY, representing motion induced by the background magnetic field. The motion on the x-axis relies directly on the motion along the y-axis. We solve the y component of the Lorentz force simultaneously and substitute it back into our primary x, omega c. This term represents the natural rate at which an ion spirals around the background magnetic field lines. The ions are caught in a feedback loop. Their forward velocity is tied to their perpendicular spiraling, giving the entire plasma fluid a mechanical inertia that resists the wave's movement. We resolve this inertia by applying the defining characteristic of hydromagnetic waves. They operate at frequencies far lower than the internal spiraling dynamics of the plasma. At the top of the next derivation, we apply that low-frequency limit. Factoring out the cyclotron ratio allows us to simplify the expression for ion velocity. Comparing this to the electron response, we see a massive discrepancy. Because electrons have so little mass, their natural cyclotron frequency is astronomically high compared to the wave frequency. This creates a mathematical collapse. Because the wave's frequency is so low relative to the electron's speed, the electron velocity term is effectively forced to 0. Substituting these velocities back into the master equation simplifies the current density J. Because the electrons effectively vanish from the transverse motion, the current is now defined exclusively by the momentum of the heavy, sluggish ions. We can now group all the intrinsic constants of those ions, density, charge, and mass, into a single term, the plasma frequency squared. The math now illustrates why the wave slows down. It is no longer propagating freely through a vacuum. Its equations are now heavily burdened by the physical mass of the ion fluid. We must now rearrange this updated dispersion relation to solve for the wave's phase velocity, which is the ratio of its frequency to its wave number. Multiplying the right side by omega squared lets us expand the fraction and break the plasma and cyclotron frequencies back down into their base physical components. By moving the wave properties to the left side, we isolate the wave's velocity from the static properties of the plasma. Here, we replace the particle-level variables, number density and ion mass, with a single macroscopic variable, mass density, or ρ. This shift moves the derivation from particle physics to pure fluid dynamics. Finally, we convert the vacuum permittivity constant into permeability, μ0, to align the math with magnetic field conventions. The derivation proves that the wave speed is dictated not by the constants of light, but by the physical density of the plasma and the strength of the background magnetic field. We apply a final assumption for astrophysical plasmas, the high-density limit. In these environments, the mass energy of the fluid vastly outweighs the magnetic energy. Because the mass density is so high, the +1 in our denominator becomes irrelevant. This simplification allows the speed of light, c, to cancel out completely from the equation. That cancellation leaves us with the final equation for the wave speed. Comparing this result to the classical equation for a wave on a mechanical string shows a perfect symmetry. The magnetic field behaves like the tension of the string, while the mass density of the ions provides the mechanical inertia. The background magnetic field provides the physical tension, and the mass of the ions resists that pull. This is why the wave slows down. It is no longer just light. It is light harnessed to matter. The electromagnetic field is forced to travel at a mere fraction of its vacuum speed, tethered to the physical movement of the ions. With the phase velocity paradox solved, we see that by embedding ion mass into Maxwell's equations, the resulting wave speed is dictated not by light constants, but by the physical density of the medium.